recording, right? Are you still? I don't know.
Okay.
Yeah.
Mm-hmm.
Hopefully,
So my name is Jennifer Le-Rademacher. I am an assistant professor in biostatistics. Welcome to the biostatistics lecture series. The topic of today's talk is longitudinal data analysis. If you attend this lecture today, you can earn up to 1 hour of continuing education. And so longitudinal data analysis is a complex topic. For an hour talk, I just want to briefly introduce the type of longitudinal data that we normally encounter in medical studies, and give a brief comparison of longitudinal studies versus cross-sectional studies. And then the main gist of the talk is about the different methods that you can use to analyze longitudinal data, and the interpretations, the differences in the interpretation when you use these different approaches. And then, when we talk about longitudinal data, missing data is a major problem. And like I said, that is a completely different topic on its own. So I would just briefly discuss different types of missing data and what you can potentially do to address these problems. And then I will summarize with some considerations that you should account for when you design or analyze longitudinal studies. And there's no financial disclosure. We have evaluations form in the back, so we appreciate any constructive criticism so we can improve future lectures. So there are different definitions of longitudinal data. Sometimes people use longitudinal data interchangeably with repeated measures. What we are talking about today is a specific type of longitudinal data where the outcomes for each subject are measured at multiple time points. And you expect the same number of time points or measurements for each subject. Sometimes it makes sense to design the study so that the measurements are taken at equally spaced intervals. It could be in log scale, it could be in linear scale. The measurements can be taken under the same conditions or different conditions. For instance, you can give a patient treatment in the beginning and then follow them under that treatment for multiple times. Or you can do a crossover study where you give them one treatment, follow them for a period of time, and then switch the treatment and measure their measurements under different conditions. But that will make the analysis and the design very complex. And then, we're not going to address that in this talk here. One advantage of longitudinal study is that it allows the study of change over time, which you don't get in cross-sectional studies. And of course, the outcomes measures can be either quantitative or qualitative. And when you have quantitative data or continuous data, the analysis is a lot simpler than if you have discrete or categorical outcomes. So this is an example of longitudinal data. So in this data set, we have 100 patients, and they were classified into two different treatments, the control and active treatment. And of course, you can collect, at the time of enrollment, you can collect basic characteristics for the patients or medical or disease status at that time. So for example, here we collected age, gender, and race information. And then the response of interest, in most longitudinal studies, you will want to measure that outcome or that measurement at the time of enrollment so that you can have some kind of baseline measure. So in this example, each patient have the response measured at enrollment, at 1 month after enrollment, at 2 months, and at 3 months. So each subject will have 4 different measurements. Yeah, and you want to make sure that every single subject will have all 4 measurements at these different time points. Yeah. So like I say, longitudinal studies are designed so that it gives you the mean to estimate the change over time. And because you collect information at enrollment at different time points, you can adjust for the variability between individuals. Let's say if you have, in the previous example, we had measurements at enrollment at 1, 2, and 3 months. So there are 3 different time points after treatment or after enrollment. If you do a longitudinal study, you'll need, let's say, n subjects. But if you do a cross-sectional studies, then you would need 3 times n subjects. So the number of subjects can increase if you use a cross-sectional study. But come with these advantages, there are disadvantages to longitudinal studies because you follow each patient for a period of time. So the follow-up time for each patient or the study will be longer than if you use a cross-sectional study. And also because you have to follow up for each patient, you have to follow the patient for a period of time. There's potential problem with missing data. So that's another consideration that make the analysis complicated. And the design will require careful thoughts, and the analysis can get complex depending on the objective of the study and also depending on the amount of missing data. So here's an example of longitudinal versus cross-sectional. So in the longitudinal setting of this study, 10 children will follow from 1 year annually up to 6 years. So for each child, you can measure the response at 1, 2, 3, up to 6 years. And then you can plot the measurements for each child, and you can connect those measurements. And so you can get a pattern of growth for each of them. Okay? So in this case, let's say if you have 10 children, if you're going to conduct a cross-sectional studies and you want 60 measurements, then you would need 60 children. And for each children, so you'll need a set of 10 children at 1 year of age, 10 children at 2 years of age, and so on. In the cross-sectional studies, you can't connect the measurements from 1 to 2 years and so on because these are not the same children. They are different children. So you can't really see a pattern of growth for each child like you would be able to do with a longitudinal study. And another things that you can see here is for each growth pattern for each child, it can vary from one child to another. And so in the analysis, if you have longitudinal data, you can adjust for the internal variability between these children. In cross-sectional studies, you can't really adjust for that because you only measure the measurement at each time point for a child. So you can get longitudinal data from either prospective or retrospective studies. Of course, with prospective studies, randomized clinical trials would be the gold standard. But a lot of times that's not feasible. So a carefully designed observational studies can be a good alternative. The advantage of prospective versus retrospective study is you can follow patients. You follow them from enrollment to the end of study. Okay. This way you can obtain better data quality because at the design stage, you can decide which time points to select to measure the response. And with careful considerations, you want to make sure you have enough measurement to address your objectives, but not too many so that you can end up with a lot of missing data. You can measure patients every month, but if you miss 3 or 4 out of 12 measurements in a year, it really doesn't do any good. So only select the time points that will make sense to answer your questions in the study. With prospective study, you can also plan the logistics of following patients to make sure that somebody will give them a phone call, ways to ensure that the patient will show up for the follow-up, or you can get the response from the patient at the follow-up time points. With retrospective studies, you don't have as much control. A lot of times the data have been collected already in a database. You only use what is available in the database. So you might not have all the time points that you wanted to use in the study. And a lot of times you cannot go back and call patients or get additional information if the information is not already in the database. Any questions before I move on to? So I think a lot of people conduct longitudinal studies, and they're not aware of the complexity of the design, the complexity of the analysis, because there are so many different methods available for longitudinal data. It is important to understand, if you use one model, what is the interpretation of the result? Okay? So it's important to understand that the study objectives will drive the design, and that will drive the analysis. It's not the other way around. So as an investigator, you need to decide up front what is it that you really want to do with a study. And then from then, you would design the study to answer that question and collect the data and use the appropriate analysis methods to analyze that data. The complications in analysis of longitudinal data come from the correlation between measurements from the same subject. Yeah, if you have measurements from two different individuals, we consider them independent. But if you have measurements from the same subject repeatedly, those measurements are correlated. So you need to take that into account. And the pattern of correlation may depend on the lag time. The two measurements that are collected at a closer lag time will probably be more correlated than measurements that were further apart. Okay? So those are the things that you can also, that you should also consider when you do the analysis. If we ignore the correlation in the analysis, you will end up with incorrect inferences or biased results at the end, or the estimates of the treatment effect may be less precise. Another complication of longitudinal study is the presence of missing data. Okay, if you have missing data and you just ignore the people with missing observations, the results may end up being biased. So for the next few slides, I want to use this example and show the different models and explain the interpretation of the different models and how one is different from another. So in this hypothetical example, a clinical trial was conducted to evaluate the effect of a meditation technique on children's ability to stay focused. So 352 children were randomized to either practice this new technique or to continue their current activity. 170 children were assigned to practice this new technique, and so that group is called the active treatment group. 182 of the children were assigned to continue their current activity. The response of interest here is the number of consecutive minutes they can stay focused on an assigned task. So the response was measured at the time of randomization, and then they will follow up at 1, 2, 3, and 4 months after randomization. So first, let's look at the summary statistics of the response here. So at the time of randomization here from this data, we see that the mean duration of focus for the active and the control group are very similar. Okay? It's about 15 minutes with a median of 10 minutes for both groups. And this is expected, right? If your randomization really worked, this is the time point before people actually start the treatment. So if randomization really works, then you will see that the outcome of interest at the time of randomization or at the time of enrollment would be similar. Okay. After 1 month of practice in the active group, you can see that the duration of focus has increased by about 10 minutes. Okay. And then after 2, 3, and 4 months, there's still, the increase is a little bit smaller than after 1 month, but it's still pretty high compared to at the time of randomization. Whereas in the control group, you can see that after 1 month, there's just a very slight increase. And then it's pretty much, stabilized around very close to the duration of focus at randomization. So this is just the descriptive or summary statistics of the response at different time points. So now we want to compare, the effect of treatment at these different time points and maybe look at how time affect the response in these groups. There are 5 common approaches to longitudinal analysis. So this is exactly why I say, it is important to understand, because there are at least 5 different approaches that are available. So you need to understand the interpretation of these different models, the pros and the cons, in order to select the correct method that will answer your study objectives. So the first method is repeated analysis, where you build separate models for each, for the response at each time point, or you can just combine the response at all the time points post-randomization and treat that as one response. Or you can also look at the response of change between time points. Okay. And of course, I'll show the examples from these different approaches. Another approach you can use is the transition models, where you model the effect at one time point adjusted for the effect from the previous time points, so based on past responses. Another model that people used to use is the multivariate analysis of variance, MANOVA. This is kind of old-fashioned, very restrictive. So in this talk, I will not illustrate this method, because what you gain in this method, you can actually do using the conditional models in method 5. And then 4 and 5, these are more flexible models that you can model the data. But they have different interpretations, and the theory behind them are a little bit different. The marginals give you the population average effect. The conditional model is a conditional effect, or the random effect model. But when you have continuous data, the results based on these 2 models are very similar. But when you have categorical data, categorical responses, these models can have very different interpretations. But a lot of times the conditional models is preferred because of certain statistical properties. Okay, so for this analysis, for this example, I'll illustrate method 1, 2, and 5. Okay, so first look at separate analyses at each time point here. So at the time, so here we just run separate models for the effect of meditation practice on focus duration. So at the first time point randomization, there's no effect. There's no difference between the 2 groups, and that's what we saw earlier. Okay, and here, before we look at the summary statistics, that was the pattern that we saw, but here we have a formal test to test that. So there's no effect at the time of randomization. After 1 month of practice, the active group focus time was increased by 8 minutes compared to the control group. You see that with a 95% confidence interval of 5 to close to 11 minutes, and the p-values is highly significant. And you see that at 2 months, the improvement is a little bit smaller, and it's still strongly significant. At 3 months, is a little bit smaller, but still significant, and at 4 months, the improvement, the difference is decreased now to about close to 4 minutes. So the effect is about 4 minutes after 4 months. It's still significant, but not as strong as in the previous time points.
Question. I'm sorry, I think I missed this. So these are the this is the delta. This is what is like 7.99?
Right. So for this particular model, it means the difference, that the delta between the estimated
of the
difference.
entire group, or the average delta for each person.
The average difference between the active group and the control group.
Okay.
And this is done separately for each time point. Okay. So here we see that we can compare the difference between the 2 groups, but separately at each time point. There's no comparison of responses between time points. Okay. So if this is what you really want to do with your study, this is the appropriate approach. If that's what you really want to do, compare the treatment at different time points separately. But a lot of times, people don't invest a lot of time to design a longitudinal study and collect longitudinal data without caring about the effect of time. But this is a very simple analysis that you can do if that's what you really want to know. Okay. Another simple analysis is to combine all the responses post-randomization and just calculate the mean. Okay. So in this case, we adjust for the baseline score because we see that the baseline between the two groups are very similar. So to include the baseline in the model, we can adjust for that. So here, for people with the same baseline score, average increase in focus duration for the active group compared to the control group is about close to 5 minutes. Okay, so this is average over the 4 post-randomization time points. Okay. And we can see that the baseline score is also strongly associated with the mean response post-randomization. And a lot of times, that's expected that the baseline measurements is highly correlated with the measurements post-treatment. So here again, it gives an estimate of the average effect, but it doesn't give you any comparison between the time points. And I'm moving on to this model. So I kind of alluded to adjusting for the baseline. Here I'm looking at again, we built separate models at each time point to look at the change from baseline. That's another way you can look at the data, right? Change from baseline to 1 month, or change from baseline to 2 months, and so on. So it gives you kind of a cumulative effect from baseline. Okay. So in this first set of models here, we model the change from baseline to 1 month. And here you can see again that with the active group, the change in active group is about 8 minutes longer than the change in the control group. And then the change go to about 6 minutes, all the way down to 3.7. So similar pattern to what we saw in the previous analyses, just a different way of looking at the data. And it has different interpretation now. Here we're looking at the effect, the change, cumulative change from baseline to the different time points that we measured the response. So here you adjust for the baseline by calculate the change. Another way you can adjust for the baseline is actually put it in the model as a predictor. Okay. So in this case, the outcome for each of these 4 models here is the focus duration at that time point. And the baseline measure is adjusted for in each of these models. So what you see here is, after 1 month of practice, people with the same baseline measure, comparing people with the same baseline measure, the active group had the focus time in the active group is 8 minutes longer than the focus time in the control group. Okay. So you see the difference in the interpretation here. When we adjust for baseline in the model as a covariate, the interpretation is comparing people with the same baseline score. This is the change. This is the treatment effect. Okay. So similarly for the other 3 models. So these models show you that there are 2 different ways you can adjust for the baseline. If you calculate the change, there's no way for you to estimate the effect of the baseline measure. If you put the baseline measure in the model, now you can estimate how much it really affects the outcome. So there's a nuance in the different ways you can calculate or you can model the responses. But both sets of these models give you the cumulative effect from baseline to separate time points. Okay, so you still can't compare the effect of time, the effect between the different time points. Any questions? Okay. So just to summarize, these separate models sometimes do not use all the information. Let's say if you model the response, the mean response, you combine the 4 different responses into one measure, so you lose some information. You can calculate the cumulative effect, but you can't really do any formal test to compare the effect of time, the response between different time points. So there's a lack of comprehensive picture of change over time. And then I also showed that the baseline measure can be included in the models in different ways, and they have different interpretation depending on if you calculate the change or you put it in the model to estimate the effect of the baseline measure. There are a couple other points that I want to make here, but we probably won't have enough time to explain much. The problem with doing separate analyses is if you have missing data, let's say at one time point you have a set of 10 patients missing. At the next time point you have a set of maybe 15 patients with missing values. And some of those patients are not the same as the one that missing the first measurement in the first time point. When you look at each time point separately, you end up looking at models for different sets of patients at each time point. Okay? So in that case, the conclusions that you make are based on different sets of patients. You don't always compare the result from the same set of patients at each time point.
Can I ask you another question? Sorry. So when you say there's a lack of comprehensive picture of change over time, your second bullet point, can you explain how, so the second example that you gave us, the analysis of mean response, so wouldn't that give you a comprehensive picture of change?
So you get a cumulative effect at each time point separately.
Actually, the example before this one.
Oh, this. Okay. So here you model the mean response of all 4 time points. You just model the average
So
treatment
it's
effect all
okay.
combined together
Okay.
to calculate the mean. Is that okay? Yeah, so, well, I'm glad you asked, so I can clarify that. So here we only look at the mean response for the 4 time points. You can calculate the sum, it still gives you
Got it.
the same model. And then the last thing is about time-varying covariates. If you're interested about time-varying covariates, we can talk about this after the presentation. So now let's move on to the next models. In transition models, we built, again, separate analysis, separate models for each time point, conditional on the response from the previous time point. So in this example, so the outcome, of course, is the duration of focus at 1 month, at 2 months, 3 months, and 4 months. And these are 4 separate models. And for each model, we adjust for the response from the immediately prior time point. So at 1 month, we adjust for the measurement at randomization. So this is exactly the same as as this model. Okay, so it's the exact same thing. Okay. At 2 months, what we adjust for is the response at month 1. So in this model, for people who have the same duration of focus at 1 month, the active group had focus duration was increased is 2.5 minutes longer than the control group. Okay, so conditional, or given that they had the same response after 1 month, this is the effect at 2 months. Similarly, if you look at 3 months, for people, so here, actually, so here, 0.63 is the association between the response at 2 months and 3 months. Okay? And after adjusting, or for the people with the same response at 2 months, the active group duration was about 2 minutes longer than the control group. Okay. Does that make sense? Okay. So in this case, if you look overall at the 4 models here, you will see that there's a strong correlation between the responses from consecutive time points. And the interpretations of the effect here, this is conditional on the response immediately prior. So for people with the same response from the immediately prior time point, this is their effect at that time point. Okay. So here you actually can see the effect conditional on the previous time point, but you can't get a cumulative effect like you would do in the separate models I showed earlier. Okay. So if what you really want to know is the additional effect based on the immediately prior response, then this is an appropriate model. Okay. If you really want to know the cumulative effect, then the separate models that I showed before for the cumulative effect would be the appropriate models. So that's the main point of this whole talk. There are a lot of different models depending on what you want to do with the studies, what your goals are. You need to use the appropriate models to answer the question.
I'm sorry to beat a dead horse, but I have a quick question. When you say cumulative, do you mean that cumulative per cohort, so control versus treatment, or do you mean cumulative per individual? I keep getting confused about
So
that.
what do you do for, in the models, you actually, the model is usually like an average for the whole, from the data. The model is pretty much the average from the data that you collect. Okay? And in this model, you actually calculate the individual change first for this change from baseline. You can calculate the actual change from the baseline for each person. And you put that in a model, then it gives you the average effect for active compared to control. For this model, you actually model the individual response from the patient, but the average effect of baseline, association from the baseline. So the baseline coefficient here gives you the average association between the baseline measure and the response at this time point. Okay? And then the coefficient here for active, that gives you the average effect. Because the models, it doesn't give you individual effect, it gives you an average. Okay, so it's like an average to model the overall formula. Where were I? Okay, so sorry. So, to summarize the transition models, like I talked about the separate models before, if you have missing data and you have different missing data for one time point, different sets of patients with with missing data from another time point, with the transition models, the different models might end up modeling different sets of patients. So the result is not consistent, if you have missing data. And another thing is, depending on how you space the measures, in most cases, if the measurements are measured at equal space, then the difference is meaningful. The additional effect after each month of measurement. Or you can do that in the log scale. In some cases, it doesn't have to be equally spaced, but it's more meaningful when it is equally spaced. The interpretation, like I say, is conditional on the previous response. It's not a cumulative effect. And so you cannot really determine the cumulative effect from the transitional models. So saving the best for last, the linear mixed model is one that is most commonly used in longitudinal data analysis. So here in the mixed models, this is a conditional model. What it can do is to actually model, adjust for the baseline, like we have seen in previous models. You can estimate the effect of treatment, and you can also estimate the effect of time. Okay. The fitting of the mixed model is, it can be complicated. So I'm not going to go into details. I just want to show the outcome from a mixed model here, and want to emphasize that using mixed models, you can estimate the effect of time. You can also, if interested or if need to, you can also model the interaction between the treatment and time as well. So it gives you a lot of flexibility. So first of all, let's look at the treatment effect. So from the mixed model, you can estimate the treatment effect as well as the time effect. So the treatment effect here, you can see at 1 month, you see that the active treatment duration of focus was 8 minutes longer than the control, and that's what we've seen in previous models. right? So the mixed models can give you the same information that you can get from other models, okay? So, I mean, everything here looks the same as what you saw in the separate analysis at each time point. Okay? So based on the mixed model, you can get that. Plus, you can estimate the time effect here, okay? Because in this model, I looked at the interaction between the treatment and time, and I see that it is significant. Okay? So based on that, I can estimate the time effect separately for the control group and for the active group. Okay? This you could not have done in the other models that I've shown so far. The other models only give you the treatment effect at each time point. Here you can calculate, and well, you can look here in the control group, the response at 2 months compared to the duration of focus at 2 months was about 0.6 minutes longer than at 1 month. And then at 3 months compared to one month, it was actually 1.5 minutes shorter, and so on. So you can do all kind of pairwise comparison between the time points. And if you look here for the p-value in the control group, there's virtually no time effect. You know, even here when you have a 0.02 p-value, if you use 0.05 as the significance level, there's so many comparisons that you would not want to use 0.05. Okay. So here to adjust for multiple comparison, I would use 0.01. So if you look at that, then virtually there's no time effect in the control group. Now, looking at the active group, you can see that the response at 2 months compared to at 1 month is very similar, okay, with a p-value of 0.69. You can compare the response at 3 versus 1, 4 versus 1. Like I say, all pairwise comparison. And here you can see that as time goes on, the response seems to decrease. And there's significant difference between these time points. Okay. So the mixed model gives you a lot of flexibility. You can estimate the treatment effect, you can estimate the time effect, and you can, you know, make any kind of time comparisons that you want to from the mixed model. Okay. So to summarize, I didn't really show the marginal model, but a lot of the flexibility in the mixed models is also applicable to the marginal model. It can handle unbalanced data. Here you can have missing data from one set of patients. From one time point, you have missing data from another set of patients from another time point. As long as you include all the available observations in the mixed models, it can handle it. Okay? And especially, you know, using the mixed models, it gives you a little bit more leeway when it comes to the assumptions of missing data. Okay, and then that's the topic of the next couple of slides. So before I go on to missing data, any questions so far? So if you can only take one thing away from this talk, what I want to emphasize is there are different models with different interpretation. Make sure you choose the right model to address the questions that you want to answer. Okay. And analysis, the example so far is just a very simple data set with no missing data at all. Just, you know, with just the treatment and the time points. And you can already have many combinations of models to choose from. You have a comment? No. So next I want to briefly talk about missing data. It's a very common problem in longitudinal studies. I think if anybody here have done a longitudinal study? Have you done any longitudinal study with no missing data? No, right? I mean, unless it's like a control lab where you observe mice for a short period of time. Otherwise, you know, if you deal with human, there will be a problem with missing data. Because subjects might drop out for a lot of different reasons. You know, people can miss an appointment, you know, for pretty much any reason, and you can't really get the information if they miss that appointment. If you completely ignore the people with missed, the subjects with missed observations, the conclusions can be biased. And the important thing is when you design the study, like I say, make sure to try to minimize missing data by selecting just the right number of observations to measure, and the time point is appropriate. If you want to measure a response, you know, and when the patient, after treatment, this is like the time of highest toxicity, people can't move, they can't come to the office, then more than likely you will have missing data for that particular time point. So you know, at the design stage, you need to think through these things and make sure you pick the time point that is feasible to collect the data. The missing data can be classified by missing completely at random, missing at random, or missing not at random. So I would define these two categories of missing data. Missing not at random, it means that the patient is missing and the response and the reason they are missing depend on the missed response, which you never observed. Okay? To handle missing not at random, you know, the best approach to do that is not clear. There are a lot of different ways to do it, but it's very complicated. So in most situations, people are willing to assume that it's missing at random. So again, missing can be intermittent. You know, patients can miss one appointment and then they show up at the next appointment. Okay, so that's considered intermittent missing values. If you have patients missing one appointment and they show up at the next appointment, a lot of times you can recover some information about why they missed the previous appointment and gives you an idea of the reason, and maybe you can you know, impute the value for the missed appointment, previously missed appointment. If you can't recover any information, that is very difficult to model or explore, because you can have, if you have 5 different time points, you can have people missing one at the first appointment, at the second appointment, a lot of different combinations. So it's hard to model the pattern of missing. So when you have intermittent missing is very difficult to deal with. Another type of missing data is dropout. So if patient missed appointment 2, then they will not show up anymore beyond that. Okay? So with dropouts, you can explore the patterns and try to understand why these patients are missing. So the different kinds of missing data, missing completely at random, this is the most restrictive assumption, where you assume that the reason for missing is completely unrelated to response. Okay, for example, patients move out area, they can't come back anymore. If it has nothing to do with the response, then you can assume that it's missing completely at random. And the subject, if you assume missing completely at random, the subject, you assume that the subjects with complete data are random sample of the whole population. Okay? So in the analysis, you can just use the complete cases, the patients with all the observations, because here you're willing to assume that people are missing have nothing to do with the response. Okay, so the people that you actually observe all the responses are just a random sample of the whole patient population. So in most cases, this is a very strong assumption and it's not realistic. Okay? But if you're willing to assume this, then any of the analyses methods that I showed before will be appropriate. Will give you the valid inferences. Missing at random is a little bit less restrictive. Missing at random assumes that the patient is missing. The reason for missing can be related to previously observed responses, but it has nothing to do with the missed response. So for example, if when you design the study, you say that if you measure toxicity at these different time points. And if the level of toxicity for the patient at time X is too low, you want to exclude that patient from the analysis or from the study. You don't want to follow the patient anymore for the study. Then in that case, the rest of the responses are missing because of the observed responses from before. Okay? So in this case, analysis excluding the cases with missing data, it means that you only use patients with very good response throughout the whole follow-up period, will give you biased results. Right? Whatever conclusions that you're drawing from the study is based on patients who can tolerate the treatment throughout the whole follow-up period. So that will give you a biased result. If you have missing at random, and if you use a likelihood approach to analyze the available cases, so for patients with some missing responses, you include the observed response in your modeling using mixed models, for instance. That would give you valid inference, just because of the statistical properties behind the mixed models approach. And if you really have missing data, I would suggest that you go work, find a statistician, somebody to help you with the data, because it can be very complicated. I think we're almost running out of time, so I'm just going through quickly here. Of course, you can, do different things to explore the mechanism of missing data to see if, why patients are dropping out. You can do the different kinds of analysis, but some of them are not appropriate. But if you use mixed models, most of the time it would take care of the missing at random assumption. So to summarize, so longitudinal studies, the advantage is it allows you to study the change over time, but it requires considerations before you even begin the study. So in the design stage, you need to determine the appropriate time points to evaluate patients. Make sure you have a good follow-up procedure in place to minimize missing data. In the analysis, there's a lot of different methods available, and make sure to choose the appropriate method to answer your questions. And what I've shown so far is complete data with quantitative outcome. If you have missing data or you have categorical data, the analysis can get very complex pretty quickly. Okay. And if time variant covariance is another issue with the data, then you definitely get more complicated. So I'm a spokesperson for Biostatistics Consulting Service. If you have longitudinal studies, please come and consult one of our statisticians in the consulting center. You can have we have free drop-in. It doesn't cost you anything. Just want to make sure, our job is to make sure the studies that you do are appropriately designed and analyzed. You don't want to spend a lot of time and effort design or conducting a study and end up with biased results or invalid conclusions. Any other questions?
Do type 1 and type 2 errors have any impact on longitudinal studies and increase over time?
If you do separate analyses, then you have to account for multiple comparisons. So you want to adjust for the type 1 error. If you do the mixed model, like I show here, it actually gives you like the overall test. So you have 4 different time points. So you have a multiple degrees of freedom test. So here it already accounts for that. Okay. So depending on practice, most people believe that if the overall test is significant, then you can look at the different pairwise comparison, and you don't have to adjust for the p-value. But some people are more conservative and think even if this is significant here, when you look at pairwise, you still need to kind of adjust for the pairwise comparison.
Thank you.
So I hand back here. Questions? Any other questions? So I really hope the main goal is for you to see that there are different models and make sure whatever models you choose will be appropriate for your objectives. Thank you.